Good morning or good afternoon, everyone. My name is Halima BELHADAD, and it is my pleasure to present my research entitled Treated versus Untreated Olive Husk in Bio-Based Concrete, a multi-scale characterization from aggregate perspective to composite performance. This work is a collaboration between the Built Environment and Sustainable Technologies Research Institute at Liverpool John Morris University in the UK and the Energy Physics Laboratory at the University of Constantine in Algeria. In this presentation, I will share how agricultural byproducts, specifically olive husk, can be integrated into concrete as bio-based aggregate. The study compares untreated and thermally treated olive husk, highlighting their impacts on the physical thermal hygric and mechanical performance of concrete. By the end of this talk, I hope to demonstrate how this underutilized resource can contribute to sustainable and eco-efficient building materials. So why olive husk? Olive husk is a fibrous byproduct generated during olive oil extraction, especially in the Mediterranean countries where olive production is a cornerstone of agriculture. It consists mainly of fibrous skin, pulp, residues, and a small fragment of olive stones. What makes it particularly interesting for construction application is its complex nature, containing both aggregate fraction represented in olive stones and fibrous fraction from olive skin and olive tree branches and leaves. Despite its abundance, olive husk has been underutilized. Most studies, not to say all of the studies, focused on olive stones rather than the olive husk. The main barrier to its use in concrete is its relatively high oil content, around 8%, generally, which can hinder bonding with cementitious matrices, affecting their hydration. Nevertheless, its fibrous morphology presents a significant opportunity. Fibers can improve thermal insulation and moisture regulations in building materials, as many studies have shown. So this research investigates whether, by carefully treating olive husk, we can overcome the limitation of its oil content while still leveraging its beneficial properties. The scope of this study is twofold. First, we conducted a detailed characterization of both untreated and thermally treated olive husk to understand their intrinsic properties. This included particle size distribution, density, porosity, and water absorption, all following the Rilem recommendation for bio aggregates. Second, we integrated these olive husk in bioconcrete matrix formulations and evaluated the resulting composites in four main performance domains: physical, thermal, hygric, and mechanical behavior. By comparing untreated and treated husk, the study aims to highlight how a simple thermal treatment can balance sustainability with structural performance, ultimately positioning olive husk as a competitive bio-based material for construction. The olive husk used in this study was sourced from a processing facility in Guelma, Algeria. The extraction process employed was a two-phase method, which preserves much of the fibrous structure of the olive husk. As illustrated in the images in this slide, the material consists of both fibrous fragments and crushed bulk olive bones. These fibers are crucial for the hydrothermal behavior of bio-based concrete, as we already stated. However, the presence of the residual oils and waxes compromises its bonding with cement. In contrast to studies that mechanically or chemically isolate the olive bones fraction, we retain the fibrous structure, which is crucial for hydrothermal performance. the core aspects of this work is the thermal treatment, of course, applied to the olive husk. The objective was not to alter the lingocellulosic structure, but rather to selectively reduce the oil content. The process was really simple. The olive husk was immersed in water at a ratio of 1 part olive husk to 10 parts water, boiled for 4 hours, and then oven dried at 65 degrees. Untreated husk, by contrast, was used as is, and the performance of both forms was directly compared later in the study. For the mixed design, the olive husk was incorporated at 20% into cementitious composites following standardized protocols. The process includes drying, sieving, and pre-soaking, preparing the husk aggregates before mixing. Proportions were carefully defined to maintain compatibility between treated and untreated samples. Samples were then cast and cured under controlled laboratory conditions. For the methods adopted here, they were guided by international standards. For the intrinsic characterization of olive husk, as we already stated, we followed the Rilem TC 236 ppm recommendation, which are specifically tailored for bio-based building materials. In terms of bioconcrete testing, we followed different standards from British to international standards, starting with bulk density, porosity, thermal parameters, and mechanical properties. These established protocols not only validate our approach, but also make the results comparable with other studies in the field. By doing so, we ensure that our findings contribute to the wider body of knowledge on bio-based aggregates and can be benchmarked against other natural bio-based products. The intrinsic characterization of the olive husk aggregates in both untreated and thermally treated forms. This analysis establishes their baseline stability as lightweight bioaggregates. The bulk density of untreated olive husk is approximately 549 kilograms per meter cube, corresponding to a porosity of about 57%. After the treatment, the bulk density decreases to 451 kilograms per meter cube, which with the porosity slightly reduced to 54%. These changes are consistent with the removal of residual oils and surface impurities, which lower the overall mass while subtly modifying the internal pore structure. Regarding the thermal conductivity, on the other hand, both untreated and treated husk exhibited a very low value, close to 0.083. These values are comparable to other plant-based aggregates such as rice husk, corn cob, and remain far below those of mineral aggregates. This confirms the potential of olive husk to act as an effective lightweight insulation filler. On the other hand, the water absorption, as we can see, shows a consistent contrasting trend. Untreated husk absorbs about 50% of its mass in water, which is really, really low compared to other materials, whereas the treated husk reached nearly 59%, a slightly decrease. A slightly increase is attributed to the exposure of hydrophilic sites once the oil residues are removed. Finally, the fiber and oil content underlying the chemical differences between the two forms. Untreated husk contains, of course, more than 8% oil residues, while the treatment reduces this to around 1.3%. The fiber content remains essentially unchanged at around 42%, confirming that the lingocellulosic structure is preserved throughout the treatment. Moving now to the composite scale, we can examine the bulk density and porosity of the concrete. The reference mix without the husk is the densest, of course, with the bulk density of about 2000 and porosity of only 21%. With the addition of 20% untreated olive husk, the density decreases remarkably to around 1400, while the porosity rises to about 36%. This confirms the strong lightweight effect of olive husk and the more open pore structure it introduces. These characteristics are particularly beneficial for thermal insulation and reducing self-weight. For the treated husk, it shows a similar trend in density, about also 1,400 kilograms per meter cube, but a slightly higher porosity of 37.2%. This indicates that the treatment improves bonding and compatibility with the cement matrix without significantly reducing the porous character of the composite. In other words, both untreated and treated husk concretes remain lightweight and highly porous compared to the reference. The key difference here is that the treated husk tends to stabilize the structure and provide better interfacial cohesion, which we will see reflected in mechanical performance. To the thermal performance of the concrete. The reference concrete has a thermal conductivity of about 1.45, which is typically for dense mineral-based concrete. With the incorporation, though, of 20% untreated olive husk, thermal conductivity decreases dramatically to 0.135. This very low value is a direct result of high porosity and fibrous nature of the olive husk, and it highlights the strong insulation capacity of this composite. Consistently, diffusivity and effusivity are also much lower, confirming that this material both conducts and exchanges heat very slowly. In the case of treated olive husk, the conductivity is a bit higher, about 400, but still far below the reference. Diffusivity and effusivity also increase compared to the untreated mix, but yet it's much lower to when we compare them to the reference concrete. Most importantly, the specific heat capacity nearly doubles, reaching around 997. This means that treated husk concretes can store more heat and therefore contribute to thermal inertia, helping to stabilize the indoor temperature over daily cycles. So in summary, untreated husk concretes prioritize thermal insulation, while treated husk concretes offer a better balance between insulation and thermal storage capacity. The buffer capacity of the concretes was evaluated according to the Nordest protocol. The reference mix without the olive husk exhibited very limited buffering ability with an MBV of only 0.21, classifying it as limited. In contrast, the incorporation of olive husk markedly enhanced hygric responsiveness. The concrete with untreated husk reached an MBV of 2.39, while the mix with untreated husk achieved a similar value of 2.18. Both are classified as excellent according to the Nordest classification, confirming the ability of olive husk concrete to buffer indoor humidity fluctuation. These improvements directly related to the higher porosity of the bioconcrete, which promotes moisture exchange with the surrounding environment. Interestingly, while the treated husk concrete has slightly higher porosity. The untreated has concrete record a higher moisture buffer value, suggesting that the presence of the of oil residues does not prevent vapor exchange in the composite scale. Overall, the results demonstrate that olive husk concretes, whether untreated or treated, provide an excellent moisture buffering performance, which is highly beneficial for passive regulation of indoor humidity and for reducing reliance on mechanical ventilation systems, especially in the Mediterranean region where this material is really abundant. Now let's turn to the mechanical performance of the composite, which is the uh, let's say the most important part of this study. The reference concrete without the husk recorded the compressive strength of nearly 37 megapascal and a flexural strength of about 8.9 megapascal, which are typical values for a conventional concrete. But when doped with the 20% untreated husk, the compressive strength dropped significantly to about 7.5 megapascal and flexural strength to 1.7 megapascal. This pronounced reduction is mainly due to the high porosity and the presence of the oil residues, which weakens the adhesion and the aggregate matrix interface. In contrast, though, the untreated husk concrete performed better with the compressive strength increasing to about 11.7 megapascal and flexural strength to 3.6 megapascal. The removal of oil residues during treatment improved the bonding with the cement paste, resulting in more robust composites. Although these strength remains below conventional concrete, of course, they are fully in line with the other bio-based concretes reported in the literature. This positions olive husk as competitive lightweight aggregate for non-load bearing and insulation application, where the trade-off between density and thermal performance and strength is crucial. Performance assessment. This table shows the classification of this study's concrete according to the Rilem lightweight concrete classification. Both untreated husk concrete BLC20 and treated husk concrete BLCT20 fall into class 2 lightweight concrete. This classification is based on compressive strength threshold above 3.5 megapascal and thermal conductivity below 0.75, both of which are clearly satisfied by the mixes. Importantly, both mixes simultaneously meet the thermal, hygric, and mechanical performance requirements, which underlines their versatility. This makes olive husk concrete particularly suitable for non-load bearing yet functional elements, such as interior partition walls or facade layers, where a balance of insulation and mechanical stability is needed. This concludes my presentation. I would like to thank my supervisors, Professor BELHADAD and Professor Anna Bras, also collaborators, and my institutions, Liverpool, John Morris University, and the University of Constantine one, for their support. Finally, I would like to thank you all for your attention. I welcome any questions or discussions on this work. Thank you.